Okay, hi everybody, and thanks for coming to my talk today. My name is Niamh Mimnagh, and I'm in my second year of my PhD as a part of the Science Foundation Ireland's Centre for Research Training in Foundations of Data Science programme. I'm working under the supervision of Dr. Raphael Morale, who is in the Department of Maths and Statistics. And today I'm going to talk to you about multi-species and mixture models and their use in estimating abundance in animal communities. Before I get on to talking to you about the mixture models, I want to talk to you for a second about why they're so important, about why being able to obtain an accurate estimate of animal population size is becoming so increasingly important, especially in areas like animal conservation and wildlife management. The Earth has experienced 5 major mass extinction events over the course of the last 500 million odd years. And these major mass extinction events are events during which at least 70% of all animal life on Earth has died. And it is pretty strongly speculated that we're currently experiencing a 6th major mass extinction event. In the last 500 years, an average of 6 species has become extinct every 10 years. And that might not seem like an awful lot, but that is 300 species in 500 years. And that's just the ones that we're sure about. The IUCN has produced what they call conservative estimates for the number of species that actually became extinct in that time. And the number is more like 800 or 900 than 300. So being able to obtain an accurate estimate of their population size is crucial if we want to be able to determine when species are starting to decline and whether the conservation efforts that we're making are proving successful at all. There are a lot of different methods for collecting data on animal population sizes. And just as an example, the one that most people seem to know about is the capture-recapture technique. And what that involves is a researcher goes out into an animal's habitat and physically catches an individual of a species, and then they mark them in some way and they let them go. And then a few days or weeks later, they come back and they do the same thing. They catch more individuals. And the animal's population size is estimated as the total number of species caught divided by the number of species that are caught on both occasions. And there are a lot of other different methods of collecting data. Some of the more modern ones include GPS tracking and satellite and aerial photography and camera traps. But all of these methods suffer from one downside, and that is that they can be quite expensive and quite labor intensive to carry out. And this is where what's called simple count data comes in quite useful. And simple count data is exactly what it sounds like. A researcher goes out into an animal's habitat for a certain period of time, and they just count the number of individuals of a certain species that they see or hear while they're out there. And this can prove to be a lot less expensive than any of the other methods that I've mentioned, but it does have one major disadvantage, and that is the issue of imperfect detection. And what imperfect detection is, it refers to the fact that the number of individuals that are observed at a certain site and the number of individuals that are actually at that site are not necessarily the same. And this can be for any number of reasons. It can be due to the animal's coloring or the animal's behavior or error on the part of the observer or even the weather on the day. There can be a lot of different reasons, but what it comes down to is that a lot of these species don't want to be seen by humans. So the population size that is observed and the actual population size that is there are not likely to be the same. So while simple count data is an attractive option, if we want to use it to estimate, to get an accurate estimate of animal population size, we need to work with it in a way that takes this imperfect detection into account. And that is what N-mixture models are for. N-mixture models are a really useful modeling technique that can be used with simple count data because imperfect detection is built directly into the model. This is the original N-mixture model. It was proposed by Royle in 2004. And this N-mixture model, it assumes that your data has been collected at several sites and that each site has been visited on more than one occasion. So it assumes that you have both spatial and temporal replication in your data. So here our spatial replication are our sites, and that is indexed by the I, and our temporal replication is the number of time points that the sites are visited, and that is indexed by T. The top layer of our hierarchy in this model are our binomial Y values, and these are the observed abundances, the raw counts that are collected during surveys. And they're assumed to follow a binomial distribution, and they rely on two different parameters, N and P. N is the actual abundance. That's the actual population size at that site. And that is our parameter of interest. That's what we want to estimate. And P is what's called the probability of detection. And the probability of detection is how imperfect detection is incorporated into these models. Say if you're in a situation where your species has a very low probability of detection, then your counts are more likely to suffer quite highly from imperfect detection than if you had a high probability of detection. And then our actual abundance, N, is assumed to follow a Poisson distribution with a rate parameter lambda, where lambda is the mean number of individuals at a certain site. Now, this original N-mixture model is used quite widely in ecology, but there are several directions in which it can be extended. And one thing that you'll notice is that this original model can only deal with one species at a time. This can't be used to model multiple species simultaneously. And that was our original goal when we started this project, was to extend this N-mixture model so that we could deal with multiple species simultaneously. And that is the model that I'm going to be talking to you about today. This is the model that we've been working on. It's a multi-species extension of that model on the last page. And similar to the original N-mixture model, we have our observed abundance, which is assumed to follow a binomial distribution, and our actual abundance, which follows a Poisson distribution. And the main difference here is that both the observed abundance and the actual abundance are allowed to vary by species. That's what this S index is telling us. And the way that we model multiple species, the way that we incorporate that into the model is we let our rate parameter of our Poisson distribution, our lambda, we let that be dependent on a random variable that we've called A. And A follows a multivariate normal distribution. And because it follows a multivariate normal distribution, it has two parameters, a mean vector mu and a covariance matrix sigma. And what this covariance matrix lets us do is it lets us go beyond just estimating the population size, and it lets us estimate the correlation between populations of different species. And this is what the correlation matrix might look like from this model in a situation where we have 10 different species. We have 10 rows and 10 columns, and each one is associated with one species. What these correlations let us do is they let us go beyond just estimating population size, and they let us start making inferences about the relationships that different species have with one another. For example, if two species have got a very high positive correlation, which you can see here by the dark blue numbers, what that tells us is that as the population size of one species increases, the other one also increases. Whereas a population of one species decreases, the other one also decreases. So that might suggest to you that maybe these two species have some kind of symbiotic relationship. Similarly, if your two species have a very large negative correlation, such as you can see here with these dark red values, that tells us that as the population size of one species is increasing, the population size of the other species is decreasing. So that might suggest to you something like maybe these two species have a predator-prey kind of relationship. And then last but not least, if the correlations are quite close to zero, that suggests that maybe these two species don't really have a relationship. Maybe they're not really found close to each other. They don't have very much to do with one another. So now that we had our model designed, we needed to make sure that it was doing what we expected it to. We wanted it to produce accurate estimates of population size and interspecies correlation. To do that, we set up a study where we simulated data and then fit our model to it. And because we were simulating the data, we knew the true values of our population size and our interspecies correlations. So we could use these, we could compare them and use them to estimate how well our estimated values are doing. We also wanted to show that our model works at different scales. So we have a small scale, a medium scale, and a large scale simulation. At our small scale simulation, we've simulated data associated with 5 species that comes from 10 sites and 5 time points. Our medium scale simulation is associated with 20 species from 50 sites and 10 time points. And our large scale simulation has data collected for 10 species at 100 sites and 10 time points. And for each of these simulations, we also wanted to be sure that our estimates would be accurate in the case of both large and small probabilities of detection and population sizes. So we've looked at the situation where we have a small probability of detection. That's when our probability of detection is between 0.1 and 0.4. And when our probability of detection is large, it lies between 0.5 and 0.9. And then our small population sizes, we've let range sort of approximately between 0 and 50. And our large population sizes, we've let range between 0 and 700. And for each of these combinations, we simulated data for 100 data sets. So that gave us a total of 1,200 data sets across our whole simulation study. We needed a way to determine how accurate our estimates were. For the probability of detection and our correlation values, we used the relative bias, and that's given by this top formula here. The relative bias of a parameter called theta is equal to the estimated value of theta minus the true value of theta, all divided by the true value of theta. And how relative bias works is if your relative bias is quite small, it's suggesting that your estimated values are quite close to your true values. And as your relative bias increases, it tells us that your estimated values are getting further and further away from your true values. And for my estimates of my population sizes, I decided to use the concordance correlation coefficient, and that's given by that bottom formula there, where mu and sigma are the mean and the standard deviation of my estimated values and my true values, and rho is Pearson's correlation coefficient. Now, the difference between the concordance correlation coefficient and Pearson's correlation coefficient is that Pearson's correlation coefficient only tells you whether two data sets have got a linear relationship. If your two data sets have got a linear relationship, but they're very different in terms of their location or their scale, Pearson's correlation coefficient will not tell you that. But because for our concordance correlation, we're mixing the Pearson's correlation coefficient with the mean and the standard deviation of both of our data sets, what that does is it means that the concordance correlation coefficient will tell you if your estimated values are different in terms of their location or their scale. These are the results that are associated with our small-scale data simulation. Here we have 4 different situations, one for each combination of small and large probability of detection and abundance. And then we have our relative bias for our probability of detection, our relative bias for our correlation, and our concordance correlation coefficient for our actual abundances. Now, when we went into this simulation, we went into it under the assumption that the situation that would produce the best estimates, the estimates that were closest to the true values, would be the situation where the probability of detection was large, but the abundance was small. So that is this situation here. And we got that for a few reasons. A lot of the work that has been published on N-mixture models deals with this kind of situation, with data where they have a large probability of abundance, a large probability of detection, and a small abundance. And also, if you remember, our small abundances ranged from 0 to 50 individuals, and our large abundances ranged from 0 to 700 individuals. And we thought that given that the range of the small values is so much smaller, that our model would be more able to estimate the values accurately. But that was not the case. And the situation that proved to give us the best estimates was the one where the probability of detection and the abundance were both large. So that is this one. And you can tell that it's giving us the best estimates because out of our 4 options, the relative bias for the probability of detection and the relative bias for the correlation are both smallest in this situation. And the concordance correlation coefficient for our actual abundances is largest. So that gave us our best estimates, and the situation that gave us the worst estimates was, I say worst, they're still good estimates. But the situation that gave us the worst estimates was when the probability of detection and the abundance were both small. And what this tells us is that when we start using this model on real-world data, that our model will work best on data that has a large probability of detection and a large abundance. Now, just very quickly before I finish up, I want to talk to you for a second about some of the other models that we've been working on, but that I'm still running the simulation study for, so I didn't talk about today. The model that I've shown you today assumes that the population is closed. And what that means is that it assumes that the population size doesn't change due to births, deaths, or migration. And that obviously only makes sense if the period of your study is very small, if your time points are all very close together. It only works if you don't give your animals a chance to breed or migrate. So we've been working on a model that relaxes that assumption through the addition of an autoregressive term, which we add onto the abundance. We let the abundance at a certain time t depend on previous abundances. And that's how we deal with that assumption. And then one other model that we've been looking at is an extension that will allow for data that has a lot of 0 values. And this data with a lot of 0 values is really common in ecology. The model that I've shown you today with the Poisson distribution on the actual abundance does not fit with data that has a lot of 0 values. So we've been working on a model that replaces that Poisson distribution with what's called a 0 altered Poisson distribution, which is much better able to deal with those inflated 0 values. And that is everything from me. Thanks for listening. If anybody's got any questions.
Feel free to pop questions in the chat there for Niamh, or to unmute and ask her directly if you like. And thank you, Niamh.
Thank you.
I have a question. Niamh, you spoke about 3 different situations, large, small and medium. Which one performed best, did you say?
Oh, yeah. So no, I didn't say. In terms of, so we know here that the best situation was when we had large probability and large abundance. That pattern repeated itself across the medium and the large scale simulations. But in terms of which of the small, medium and large scale simulations produced the best estimates, that depends on the, I'll just go back a second. That depends on the number of sites and the number of species. So if we look at our multivariate normal A here, it's an S-dimensional normal distribution. So what that means is that every draw from A is an S-dimensional vector. And we have one draw from A for each of our sites. So the best estimates of A are going to be when we have a large number of sites and a small number of species. So that meant that in our large scale simulation, we had 10 species and 100 sites. And in our medium scale simulation, we doubled the number of species and we halved the number of sites. So what that meant was that the large scale simulation produced the most accurate results. Does that make sense?
Yeah, that's great. Thanks a million.
Cool. Thank you.
I see a question in the chat, Niamh, there. It's from Dara. It's such an interesting project. You use the binomial and Poisson distributions in your mixture model. Do they have some specific features that make them useful for your problem?
Yes, good question. So to answer that, I guess we need to go back to what the definition of these distributions is. And I'll start with the Poisson distribution. The Poisson distribution is used to model the number of events that happen in a certain time period or in a certain space. So when we're learning it in class, we always look at the number of buses you expect to arrive in a certain amount of time. But in our case, the event is an individual of a species being present. So the actual abundance is, yeah, so that's how the Poisson distribution fits the actual abundance. And then the binomial distribution is the number of successes that you would expect when you have n trials and a probability of success p. So here a success is that you have observed one individual of a species. Does that make sense?
Okay, is anybody, any other questions for Niamh?
When you said zeros are common in ecology data sets, what is that because it's common not to see anything when you go out to a site? Or?
Yes, yeah, it's very common not to see anything.
And what's the definition of a site? Is it like a walk along a forest trail, or?
It depends on your data set. Yes. Yeah, I think it's different between data sets, but yeah, it's okay. A sort of a patch of land that is however big, depending.
Okay.
I don't see any other questions in chat. Does anybody else want to ask Niamh a question? Feel free to unmute.
I'll sneak in another one. Do you have any sites, or do you have any real data sets you can use, or any in the future? Are there any specific?
Yeah, it's sort of a work in. Oh, sorry. It's sort of a work in progress at the moment. We're trying to look for data that's sort of suitable. There is a large-scale survey that's carried out in America every year. It's called the North American Breeding Bird Survey. And we can use that data. I'm currently fitting this model to that data. So I'm currently, I'm looking at a data set that has got data for bald eagles and then data for a lot of birds that bald eagles are known to prey on. And I'm hoping that gives us good results, because you would expect that there would be negative correlations between the bald eagle and the bald eagle's prey.
Cool. My parents fill out a garden bird survey. They have to mark which birds they see in the garden. I don't know.
Oh, that's cool.
Okay. Any final questions for Niamh? Or do you have any final comments you want to make, Niamh, to the group?
No, I think that's everything from me. I'd like to thank everybody for coming to my talk. I'd like to thank, I'll stop sharing. I'd like to thank the library team for hosting this. And yeah, that's about it for me.
Right, and our thanks to you, Niamh, as well, for coming on and speaking to us today about your work. It was great to hear about it, and thanks to everybody for attending as well. Really appreciate the support for Love Data Week. So virtual round of applause to you, Niamh. Thank you so much. And great to see you again.
You too.